Oliver Neukum, and he will talk to us about the state of USB 3.0.
Good morning from me again. So I am going to talk about USB 3.0 today. And I'll first talk about the new things in the standard, then about what the host control implementation does, a few related miscellaneous things that are too nice to miss out, what your kernel can do for you, and more importantly, where it still needs your help, and a short outlook about what is probably going to happen in USB land after 3.0. So let's begin with the standard itself. Well, it features what you all like, more speed. As those things are growing in size, our speed has to increase as well, or at one point we would be unable to get our data on them or off them. It improves power management, so we can use less power although we increase speed. It provides more power per port, which is something very many people always keep asking about. I want more power. And it does quicker enumeration of devices. This allows faster boot times, obviously. It's mostly done in hardware, so I won't talk any more about it. So, speed improvements. There are basically three major ways of increasing speed. First and foremost, we've changed the wire protocol. We've introduced a new feature called Stream Support, about which I will talk a bit in detail later. And we've softened the concept of master and slave. Under USB 2.0, a device spoke only when spoken to. This has the obvious advantage that there is no question of arbitration on the bus, and has the necessary disadvantage that the host had to ask even if there was no data available, which means bandwidth is wasted and power is wasted. We don't do that anymore. So, the wire speed has gone to 5 gigabits per second. That has basically been achieved by stealing the wire protocol from eSATA. And the bus is now full duplex. So in theory, you can do 10 gigabits per second, only in theory. And we now finally provide 900 milliamps per second, per socket, not per second. Wouldn't make so much sense, per socket. A major change in the architecture has happened. It has become more complex. A USB 2.0 device was, in principle, quite simple. The device itself had interfaces, and the interfaces have endpoints. The endpoints are not shown in this graphics. It would have been too cluttered. And I/O is done to the interfaces, and anything related to management of the device, power management, resetting, enumeration, choice of configuration, and so on, is done at the device level. It was true there are association descriptors in 2.0 devices, like in this one here. It's mandatory in that case. Cell phones do have an interface association between the control interface for the wireless network and the wireless network itself. 3.0 has become baroque. The devices have a thing called functions, a very badly chosen name, but that it is. The functions themselves have interfaces. The interfaces, like in 2.0, do have endpoints. And the endpoints, well, some of them, the bulk endpoints, do have streams. You can think of the function more or less as the descendant of the association descriptor. The major change in the device model is that the power management has been split and is done on the device and the function level. I'll talk about that a little bit later. I/O still goes on to the endpoints of interfaces. Well, as I mentioned, the the power management function has been split. It has been split at the location that it is done and at the functionality it provides. We now can suspend the function. A bit hard to understand, but imagine, for example, you had a camera which can do images, sound, and has a card reader. You'd take the card reader in one function and the image sensor and the sound sensor in another. And if you want to access the card reader, you can shut down the imaging part or vice versa. That helps to save power. What more we can do is that we can now suspend the link to the device and leave the device itself on. At 5 gigabits, the amount of power the link itself draws can dwarf easily what the device in its function will consume. The link power management itself was introduced in 2.0, but rarely used and not very good. In 3.0, we do have two sleep levels for the link power management, U1 and U2. The only difference is, again, latency versus power saving. It is done in hardware. Hubs can do it to their attached devices, and devices themselves can request that the link be put in the link power management state. Furthermore, we have the latency tolerancing messaging, which is more or less about devices telling the host how much power management they can cope with. I'll have a separate slide for that. And furthermore, USB 2.0 was a broadcast bus. Anything the host said was attributed with the device address and sent out to the bus. Everybody could listen on it, and that also wasted power. We don't do that anymore. The stream support. That is one of the, frankly, hyped features. It has been specifically more or less created for storage devices. Come in, come in. I don't bite. Oh, thank you. Okay, what is a stream? A stream is an attribute of a bulk endpoint, and more or less is just a means to multiplex traffic to the endpoint. Why would I do that? After all, I could just send more data to the endpoint itself. It allows you to give additional meaning to the data transfer. It says you might have a protocol that connects function is a bad word here. Purpose A with one stream ID and purpose B with another stream ID, and you can cope with one endpoint. That is a nice advantage because endpoints are limited in number. You can have only 16 per device, and changing that would have meant changing all commands because the endpoint ID is hard-coded in 4-bit. On a technical level, a stream is just a number. The stream ID, it's a 16-bit number, and you tell the endpoint, no, this is not going to your default stream, but to some other. And the endpoint deals with this. This feature itself is a part of the standard, but devices can tell the host how many streams can I support, and that number can be 1, so in that sense, streams are optional. I will have a slide for UAS where I can tell you how this is actually used in practice. Now, let us come to the extensible host controller interface. The extensible host controller interface is the successor of the enhanced host control interface, which explains why the abbreviation uses the X from the from the inside of the word, not the E, was already taken. The XHCI is a new design, and it's probably going to be the only one. It is already so complex that making an alternative implementation would be very, very hard. And at the speeds involved, it needs to have some complexity. So doing a real different implementation would not be helpful. It does have one major design trend. Functionality is put into the hardware. Under 2.0, you tell the controller, transfer please this amount of data taken from that buffer to an endpoint at a given device address, and the controller does that without any regard for whether this device is actually on the bus, it does have that endpoint, or whatever. It just follows orders. Under the XHCI controller, you need to first tell the controller there is this device and it has these endpoints and they are supposed to work at that data rate and so on. All those features are tracked in hardware. Furthermore, the bus addresses for 2.0 devices, 3.0 devices don't actually have bus addresses in that sense, are also assigned by the hardware. You actually tell the controller, give that device an address, and it generates the commands itself, puts them over the bus, and so on. And we do manage now the bandwidth of the bus in hardware. Well, except Ivy Bridge. I guess they didn't finish in time. So for that controller, we do have software implementation. So why is all this done? This is very unusual for Intel. Usually they make very Spartan controllers. It's done because all those features, the bandwidth and the bus address, are common to the whole bus. So if you do them in hardware, there has to be no controlling instance in software for the bus, and virtualization becomes very easy. You can take a device and assign it to one VM, the other device to the next VM, and if that takes too much bandwidth, well, then the second VM gets an error, but there needs to be no communication between the VMs. And there are even special commands in the controller for virtualization. And for the same reason, we have eliminated the companion controllers. All traffic even to the legacy devices, 2.0, 1.1, are handled by the XHCI controller. In hardware, you can usually, by some vendor-specific register, switch over the ports between the EHCI and the XHCI, but you do that on boot only, and then it's final. As a further nice feature for the programmer, you have a total scatter-gather wherever you want in 64-bit, and you have total control over interrupt generation. And to make it even better, the link power management is also done in hardware. You just set the timeouts, and that's it. So I figured it might be beneficial to explain a bit how a USB controller is used in hardware. Do come in. If you write a device driver, you don't actually have to know this because the USB core will do it all for you. But to understand the features of the controller, it is helpful. You just create a buffer in main memory, fill it with your payload, and you tell the controller to transfer it. You do that by writing a sort of command into the main memory, which contains the address and length of the buffer, and the rudimentary description of what's to be done with it. And the host controller then walks its list of commands, executes them, and if the bit for generate an interrupt is set, then it generates an interrupt. And before it generates the interrupt, it writes the result in yet another special data structure, all in main memory. The all in main memory is a crucial feature because it allows you to get away without PCI accesses. And PCI accesses are becoming more and more expensive in terms of performance. And for us to be nice, the buffer, again, as I mentioned, can be anywhere in main memory. It's got 64-bit pointers, and you can segment your buffer however you want. So that was what was to be said about the implementation itself. I'm now not coming to two features, UAS, USB attached SCSI, and the support for USB in ACPI. They are strictly speaking not part of USB 3.0, but they fit extremely well into the software framework as it is now done. And they are a great example of how to use the features of USB 3.0, especially the streams features. So I am going to say something about them right now here. The complaints we had. Why is my USB storage dongle so slow? Well, it was not because USB 2.0 is slow. It's 480 megabits per second. That's still quite fast. It was the fault of the protocol. The protocol for USB storage was originally developed for floppies, and that shows. If you send a command to a storage device, you send a command, you send the payload, you retrieve the result, you evaluate the result, and then you go on again. And of course, while you evaluated the result, you've missed the next time slot to send the next command, and it becomes even more slower. Well, what I was to tell you, there is no command queuing. You execute one command at a time. That naturally means you execute the commands in the order you send them to the device. How else could it be? There is only one command for the device to execute. And to make it even worse, you cannot send the next command while the payload is underway. No, it all goes to the same set of endpoints. So all three phases cannot overlap and have to be executed in that order. And it's even worse. We don't use the native error handling. To be fair, we can't. It would disallow us from making SCSI to USB bridges, but that means that actually the result has to be evaluated before the next command. And to make matters even more worse, we use a kernel thread, and that gets us the scheduling delays. So I guess you have now understood why our USB storage devices are so slow. So, what could be done? We could eliminate the kernel thread, yes, but that would be a very major change for relatively little gain because the protocol would still suck. So, we have USB attached SCSI, and it is fast, mainly by allowing multiple commands. And they can be executed out of order. Technically speaking, this is governed by the rules of SAM4 from the SCSI standard. And we've separated the endpoints so we can send the next command while we still retrieve a payload on the upload on another command. There is one major drawback if you do such a thing. You have to know for which command am I retrieving the result or sending the payload. Because if you mix them up, then your disk is... There is no nice word for this. let's say, irretrievable. So we gave every command a number. That is what attack just is. It is unique, and it is 16-bit. And I mentioned this, stream IDs are 16-bit. So there you now see what we use the streams for. A stream is just a command on the URS level. So this was our nice hack for using streams for storage devices. And there is another improvement. As I told you, USB 3.0 softens the strict master-slave. A device now can tell, I have data, please speak to me. And the host will do so. And that facilitates the out-of-order execution of commands. Very well. ACPI and USB. Why do we need it? Because we do know nothing about our ports, and we cannot switch off the power to ports on the main board. We all know it is possible, because our laptops cut power when we sleep, but for some magic happening in BIOS, they don't do this if we use USB devices as wake-up sources. So it must be possible. What has happened? We have added support for USB in ACPI. Strictly speaking, in ACPI 3.0. And how does it work in detail? We have associated features with the ports on the motherboard. Firstly, a port can be usable or unusable. You now should ask, why can there be unusable ports in your computer? Well, the number of ports in your chipset is set by the manufacturer. But not every mainboard leads every port to the outside. Some of them are used for internal devices, like your webcam, your Bluetooth, your card reader on this laptop, your fingerprint reader, but some are simply left dangling. They are marked in the BIOS as unused, and because we can now cut power to ports on the mainboard, we simply cut their power, don't have to worry about them anymore, and we don't use the power. The second attribute is the pluggable versus unpluggable. On an external port, I can obviously put in a device. That's its reason for existence. But this is also possible for some internal ports. My fingerprint reader is always cabled to the same port. So is my webcam. But not my BT USB device, which does my Bluetooth. When I hit my RF kill key, it will go away. And if I hit it again, it will come back. So it is internal, but pluggable. I have to run the hot plug detection on it, or I would miss the unplug and replug events. So, what do we do with it? We export these attributes to user space, so the GUI can do something more or less sensible with it. And we extend the auto-suspend mechanism. You can tell the auto-suspend whether to simply and nicely suspend your device or to cut power to the port. And if you cut power to the port, there will be no more hot plug detection. That is the trade-off you have to make. And last but not least, USB gained by doing the ACPI standards methods for powering and depowering ports on the motherboard. On hubs, we already could do it. That's part of the standard command set. Now, the nice part. What can your kernel do for you, and what should you do for your kernel? Let me begin with what our kernel still cannot do, because I hope, but do not, well, I hope that some of you will add support for it. What's missing? the functions in the architecture. They are there, part of the standard. Every USB 3.0 device does have at least one function, but we usually don't do something with it. What does that mean? If you write a driver for a USB device in the kernel, you are not writing a driver for a device. You are writing a driver for an interface. There is also a driver for devices. It is one driver, it's called the generic driver, which does very little but distributes events to the interface drivers. For us to use this, we would need a generic driver for functions. It's not been done. Another nice little feature missing would be how to do IRQs without doing PCI access. As I mentioned already in an earlier slide, the controller does write the results of its operation in special event data structures. We could evaluate them instead of the PCI registers of the controller. In case it's not an external event that triggered the interrupt, which would not do an event data structure, we could do without a PCI access. Our speed would more than double in the interrupt handler. What is done right now? Right now, we are introducing link power management even for USB 2.0 devices, which will save some power. What has been done recently is in 3.9, we finally got working UAS support. Working in that sense means it will survive the first error. It didn't before that. Recently we did the ACPI support I talked about, but we're still missing a user space component. We did latency tolerance messaging, which the kernel now can do since 3.6. Again, we are missing the user space component. And in 3.5, we added the link power management support for USB devices. And that is about what we added in the last 18 months. So let me go to the details. Function support. We do have a generic device model in the kernel, which does have PCI, that's the bus, to which is attached the host controller, to which is attached the device, to which is attached the interface. Your generic driver, as I mentioned, is for the interface. And there is a generic driver for the device, which handles things like reset, telling each device to prepare for a reset. And then again, we have reset the device now. You can resume your function, your interface. Sorry. What we would need to do is to write this again for the function so that the device tells the function to do something and the function tells its interfaces. This unfortunately means a rather extensive change in the generic driver model, so we don't have done it right now because there has, for now, been little reason to do it. We have not seen a multifunction device in the wild. This is probably because USB 2.0 does not do functions, and people want to maintain backwards and forwards compatibility. So right now it is not being used. But this is likely to change. There we would need your support. If there is any hacker for the generic device model here, you know what you need to do. Yes, I mean you. What have we added? There is the feature has no official name, so I'm calling it the Zero Power Auto Suspend. What does it do? It switches off devices. Let me explain the reasoning behind it. It may be a tautological conclusion here, but you cannot use less than no power. Sounds paradox. Doesn't matter, when Greece they invented the concept. But That means if you can cut power to your device, you do have ultimate power management. You can't get any better. So let us examine what do devices need power for. While they work, of course, they need power for their operations, and the USB bus, as a bus, needs power to detect hot plugs. Has a device come? Has it gone? On USB, you need power for that. There are bus systems which can optionally do it without power, for example, eSATA, but USB is not among them. You do need to power your port to detect hot plugs. So, which devices can live without power? Of course, not the operational devices, but those who don't need hot plug. As I mentioned, we have now XHCI support which tells us whether a device can be hot plugged at all. We use that information in the kernel. If it is hot plugged, then we cannot cut power. Or alternatively, we export the attributes for power management, and if the user tells us we don't care about hot plug detection, then we cut power. Furthermore, devices need standby power. We had this nice bug about the drive enclosures which lost data. It turned out that they do have an internal cache, and if you suspend the device, they clean the cache. Great. The fix was to issue a flush cache command on the SCSI level before you suspend the device, but this should illustrate that devices do need their standby power. At least some devices do need it. What can we do? We made an educated guess. If a device does do remote wake up, for example, your usual mouse does it. If you press a mouse button, it can wake up the system. Then you need power. It's an indisputable thing. To do remote up, you need to be able to do remote wake up, you need power. So you also need power to retain state. But in the normal course of operation, your system does already lose power. It does so when you suspend to disk. And USB devices do have a support function for suspending to disk. It's called the reset resume operation. It's used for S4. So we figured if a device does not need hot plug detection, can deal with S4, and does not do remote wake up, then we cut its power when it's suspended. That is the heuristics we are using today. It is quite new. Whether it will work in the future, we need to see. And we would like from you testing and some support for ignoring remote wake up or hot plug events in the GUI. LTM support. Let's say I have a USB microphone. It's imaginary, this is not. Then it has some internal buffer. While we record, that buffer is filled, and from time to time it has to be transferred to the host. For power management, we would like to do these transfers as rarely as possible, because whenever we transfer, the bus cannot be in a power suspend state. So, what do we need? We need to know how large is the buffer. That itself would not be a good information, because we would need to compute how fast the device fills its buffer. No, we need to know how long can this device do without being serviced. That's the latency tolerance messaging. The device tells the host, I can do for these many milliseconds without data transfer with you. The host takes this information, computes from it how long would it take to talk to this device. This is not identical because there may be hubs in between and you need to wake up the port on the main board. And from that, it computes a time for telling user space how long this device can do without I/O. The kernel part of this feature is done. We export those computed hints over usbfs. What we would like to do would be the multimedia frameworks, Pulse Audio and its relatives, to use them and schedule their I/O based on this. It would help us save power. So, as I've talked a lot and 10 minutes left or so, let's make this quick. It might interest you what comes after we've finished with what we are already doing and what is still missing. So we are seeing that the logical kind of links are becoming divorced from the physical kind of links. For USB, you already have the physical port. You have in your laptop a mini PCIe slot, which already can do USB. It now can be done over HDMI. For other protocols, you see the same. We expect that we will see less kinds of interfaces in the future. In my personal opinion, for example, FireWire is dead. And what we've also found is that people don't like wires. In every conference, there is somebody cursing that while he can have Wi-Fi, he cannot have wireless power. I'm sorry to say that that problem is unlikely to be solved soon, but he might have wireless USB. Wireless USB already exists, but nobody's using it. This is probably a result of nobody using ultra-wideband. Ultra-wideband has its problems. It needs its own controller. That costs, so we should use the controller that is already on the motherboard. That's your Wi-Fi controller. Unfortunately, right now we can't. Your Wi-Fi has a total schedule. It's linked in the access point. We can't deviate from that, and it's too slow. So what do we need? A fast link, a link under our own control so we can do real-time I/O, and we really would like somebody else to do our security stuff, which means Wi-Fi would do the job. If it would have a dedicated channel and would be fast. So now we are going to 802.11ad. Sorry, this is a tongue twister, which meets these requirements. It allows you to do something else but wireless LAN over the Wi-Fi link. It provides its security like every form of Wi-Fi, and it has a dedicated link between its nodes. It does have access points, yes, but you don't need to use them. It operates at 60 gigahertz. It uses a directional antenna, yes. Electronically, you can electronically switch the beam by using a phased array antenna. You can run a serial bus over it by an extension. And we got indications that people are going to use it for docking stations, which contain a USB hub. That's our primary use case and will be the first implementation of this new standard. It's unfortunately not yet fully public. You can read about the existence of 811AD in the standards bodies. You can look up the wireless serial extension. They will tell you it exists and it does this and that, but not how. Sorry. Well, we are SUSE, we are great. Well, I have to show this. And if you like to work for us, please do so. We are cool, and I haven't bitten anybody since April. So don't fear, come to us. Questions? Somebody will give you the microphone.
Hello. Unplugging a USB device without having first unmounted or ejected through software, is it dangerous for the device to damage its hardware?
No. What you can damage is your data. If you unplug the device, of course, you depower it, and if you have anything buffered, that's gone. But the specification tells you you can unplug a device at any time under any condition. No problem.
Thank you.
Well, any questions over the IRC channel? No? Then I guess we'll finish with a few minutes to spare. Time to get a coffee. Thank you. We still have a question? Sorry.
I would like to know if it is possible to use USB for accessing memory as firewall device. Closer? As a FireWire bus is known to be exploitable. If it is possible to use USB this way, if a USB device can anyhow affect which memory region will be read.
Short answer, no. Under FireWire, a device can request a transfer. Under USB, it cannot do so. The transfer has to be initiated by the host. The only function a device has in that is that it indicates that it is ready to transfer. And it can do that on its own initiative, but it cannot start a transfer. The buffer is still set up by the host, and if the device sends an unsolicited ready event, then it will be ignored. So there is no danger in that regard. So, anybody still overlooked? Because this is embarrassing. No? Shit. Yeah.
I guess this is it. Thank you, Oliver.
Okay, then let's have a coffee or something.